Have you ever wondered why a spacecraft returning from the moon directly enters the Earth's atmosphere with huge amounts of thermal heating to be taken care of by the heat shield? Why doesn't it enter an Earth orbit, dock with the ISS or other space station, and then the astronauts just return normally? Returning from the moon, the spacecraft needs to slow down by about 3,200 meters per second to enter an Earth orbit which aligns with one of the space stations. This creates a huge fuel penalty, and not just for the stage that needs to slow down. This also creates a fuel penalty for the upper stage that needs to insert lunar insertion to the moon. And it creates another fuel penalty for the huge first stage with boosters that needs to lift the upper stage and the stage which we call the command and service module for the rest of the burns. So let's have a look graphically how this would work out for an idealized mission. To launch from the surface of the Earth to LEO takes about 9,500 meters per second of delta V, including things such as gravity losses and drag. Then, from LEO, a TLI of about 3,200 meters per second is required. Then, when it gets to the moon, there's a further about 600 to get into a near rectilinear halo orbit, and about another 600 to get back out. That's the current option. The second option requires an additional 3,200 or so to enter a Earth orbit to be able to dock with the space station. Now let's break this down, how this extra fuel impacts the size of each stage. So using here the rocket equation, what I've done is I've broken this up into the three stages, methyl-ox for the first two and hypergolic for the upper stage, with a 15-ton command module that includes life support, heat shield, and obviously space for the crew. Now let's have a look at it as a chart. These here show each stage, its fuel, and the mass that the engine has to do. So if you look at the current and you look at the Earth insertion, there is a significant difference. Now, I've based these with a 10% tankage for the upper stage and the command and service module, and a 15% tankage for the first stage. Now, let's have a look at it in terms of stage by stage. So on the left, we have the aerobraking, and on the right, we have the Earth insertion. Have a look at the difference in terms of fuel and the total size. It becomes very quickly apparent that the total mass would be 2.8 or almost 2.9 times greater for that extra 23% of delta V required. Now here's the real kicker. You'd still have to have a heat shield. Why? Because if you're coming back to the Earth and there was a propellant leak, or for some reason your engines didn't fire, you would still need a backup heat shield. Otherwise, it would be catastrophic for crew and spacecraft. Now, this is my idealized rocket. The rocket would have actually a very similar mass to orbit efficiency as a Saturn V and the SOS Block 1B. But if you want to change the numbers around, or you feel something should change, drop a note and let us know.